In this video tutorial, we will be introducing the mole concept. Now, before we begin, it is important that we understand the difference between the terms atoms, elements, molecules, and compounds. A common mistake is that students think that the word atoms and elements are the same thing. That's not true. All elements are atoms, but not all atoms are the same element. That's like saying all Chinese people are humans, but not all humans are Chinese. So an element is a type of atom, but an atom is not an element. When we talk about compounds, we are referring to two or more different elements that are chemically combined together. If they are bonded covalently, typically we use the term molecules, but if they're bonded ionically, we typically use the term formula unit instead. If you're not sure what the difference is, please watch my videos in Unit 1. There's an extensive video on molecule versus formula unit, when to use one term versus the other. Now if you look at this example down here, how many atoms are in diagrams A, B, and C? Well, here I have 3 atoms in this particular particle, and there are 11 of these particles altogether. So 3 times 11 makes 33 atoms. In part B, there are 2 types of atoms, so we're just going to count them all, and we have 23 of them. And then in C, we have 2 atoms in this particle, but 6 atoms in this particle. So 2, 4, 6, 8, plus 6 and 6 and 6 and 6, and that gives us 32. The question then asks, how many types of elements are in diagrams A, B, and C? Now because this sheet doesn't have any color, there's really only 2 types, white and black. So in each case, we have 2 types of elements in A, B, and C, the white and the black ones. It then goes on to ask how many types of compounds are in diagrams A, B, and C. Well, here there's only 1 type, 2 white, 1 black, 2 white, 1 black, 2 white, 1 black. While in B, there are no compounds, there are no groupings of atoms, it's just individual atoms together. So we would say 0. And then in C, there's only 1 type of compound. This is not considered to be a compound, it's considered to be a diatomic element. In order to be a compound, it must have 2 or more different elements chemically combined. This is just one same element chemically combined, so it's just an element. So there's only 1 compound, 2 black, 4 white, 2 black, 4 white, 2 black, 4 white, 2 black, 4 white. So just 1. Alright. Question number 4 then says, how many compounds are in A, B, and C? Well, over here there are 11 compounds. While down here there are no compounds. And up here there are 4 compounds. Alright, so it's important that you be able to differentiate between the word atoms, elements, and compounds, types of compounds versus number of compounds. So you'll have to read carefully the questions in this unit because they may ask you different things, even though the wordings may appear similar. So in part A, 33 atoms, but only 2 types of atoms, the elements, white and black. There's only 1 type of compound present, but there are 11 of them. So read those questions very, very carefully. Just changing the wording slightly changes the entire meaning of the question. Now visualizing it makes it a lot easier to determine these values over here, but there's no way you're going to draw every single atom during your calculations. So instead we must rely on the chemical formula. So when you have a coefficient of a 3 in the front, you're saying that you have 3 of these H2S's. H2S, 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 3 of them. Whereas if I put a 5 as a coefficient, I'm saying that there are 5 of these Na3PO4s. Na3PO4, Na3PO4, etc., 5 of them. So let's try to do this exact same activity, but instead of using pictures, you need to rely on their chemical formula. Alright, let's take a look at the first one over here. So water has 3 atoms in each molecule. 2 H's, 1 O, so 3 atoms. But because I have 6 water molecules, I need to multiply that by 3 to give me 18. 18 atoms. Well, how many compounds are there? Because I have 6 of these molecules, I have 6 compounds. Now, how many types of elements are present? There's only 2 types, hydrogen and oxygen. And finally, how many oxygen atoms are present? Well, if I have 6 molecules and 1 oxygen per molecule, 1 times 6 equals 6. Alright, what I want you to do is try the rest out yourself and then press pause. When you're ready, press play and we'll take it up together. Well, technically I don't have to take it up because the answers are all at the bottom, but whatever, let's try it out anyway. So each of these compounds has a lithium, a bromine, and 3 oxygens. That's 5 atoms. But since there are 2 of these lithium bromates, I have to multiply by 2. 2 times 5 equals 10 atoms. What's it asking next? Compounds. Okay. So how many compounds are there? Because there's 2 of these lithium bromates, the answer is 2. Now, how many types of elements are there? Well, there's the lithium, there's the bromine, and there's the oxygen. So there's only 3 types. And finally, how many oxygen atoms are there? Well, 2 times 3 equals 6. All right, let's do these other ones real quick. Atoms, there are 3 in sodium hydroxide, 1, 2, and 3, times 3 of them all together gives you 9. How many compounds are there? Well, that says 3. 3 sodium hydroxides, 3 compounds. How many types of elements are there? Sodium type, oxygen type, hydrogen type, so 3. Finally, how many oxygen atoms? 3 times 1 oxygen, 3. The calcium hydroxide, there are 2 oxygens, 2 hydrogens, and 1 calcium, so 5 of them. 5 atoms. And there's no number in the front, so we just leave it as 5. How many compounds? Again, no number in the front, so we always assume a 1, so there's only 1 compound of calcium hydroxide. There are only 3 types of elements, the calcium, oxygen, hydrogen, and only 2 of the oxygen atoms, because 2 times 1, where we multiply everything into the bracket. I think you're starting to get the pattern now, so let's just do one more over here. So how many atoms are there? Well, there's 12 carbons, 22 hydrogens, 11 oxygens. So that's 45 atoms in one molecule here. But since there's 2 molecules, 45 times 2 is 90. Since the coefficient is a 2, I have 2 of these molecules. There's only 2 compounds. There are 3 types of elements here, a carbon, a hydrogen, and oxygen elements. And finally, with 11 oxygens in each molecule, but 2 molecules in total, 2 times 11, 22 oxygen atoms. Alright, so try these other ones yourself. Verify your answers at the bottom. If you have any questions, please come see me. Now, if you recall, the law of conservation of mass states that atoms are neither created nor are they destroyed during a chemical reaction. All that happens is that they are rearranged into a new form. That is why we have to balance our equations so that they follow the law of conservation of mass. It's not good enough just to write down the elements. Hydrogen plus oxygen makes water and monatomic oxygen. You're not allowed to have an extra piece just lying around. Oxygen is diatomic and it must be bonded to someone else in order to remain stable. And that is why we put the coefficients in the front so that all the atoms going in are the same number of atoms going out and everybody is stable and accounted for. So for this reaction to work, I need 2 of these hydrogen molecules, 1 of these oxygen molecules, and in return, 2 of these water molecules will pop out. So balancing the equation helps us to understand how many of each chemical compound is involved in the chemical reaction. But there's a problem. Atoms and molecules and compounds are much too small to react them 2 at a time. Just to give you a comparison, the tip of a needle contains 80 quintillion atoms. That's 18 zeros after the 80. So how are you supposed to keep track of just 2 hydrogen molecules reacting with just 1 oxygen molecule to make 2 water molecules? When you're dealing with quintillions of quintillions of quintillions all at once, it's just not practical to work with them at such a small scale. So instead, we like to group things together because extremely large numbers are usually meaningless to most people. For instance, if I told you that a child is 1,051,200 minutes old, what kind of birthday gift would be appropriate for a kid this old? Well, this number is kind of meaningless. It's too big. I mean, I have a hard time when I'm talking to other parents and they're saying, oh, my kid's 19 months old. Then I have to go, oh, 19 months, subtract 12. Oh, 1.5 years old. And 19 is such a small number already. 1,051,200 minutes old. What is that even? All right, people like to group things by the dozen, and a dozen is 12. So if I divide this number by 12, I end up with 87,600 dozen minutes old. Did that really help you much? It certainly doesn't help me. So I need to group things by an even bigger number. Well, 525,600 minutes is equivalent to 1 year. So if I group the minutes by year, well, 1,051,200 minutes divided by 525,600 minutes gives me 2 years. And the number 2 is a much easier number for me to visualize, for me to relate to, than 525,600 or 1,051,200. This is the benefit of grouping things together so that super large meaningless numbers become smaller, more easier to deal with, and most importantly, relatable to us, meaningful to us as humans. So, when it comes to dealing with super ridiculously large numbers, it's easier for us to work with them if we group them together. But grouping them together by things like, for instance, the dozen, might not be helpful because the dozen is too small. It still provides us with a pretty large number, one that still holds very little meaning for us. So to fight big numbers, we need to use big numbers. And that's where the mole comes in. The mole, also known as Avogadro's number, so number, Avogadro, is 6.02 times 10 to the power 23. We like to group atoms together in this large grouping. Now, this value is experimentally derived, so it's not exactly 6.02 times 10 to the power 23, but we'll take this one as 3 sig figs is usually good enough for our calculations. Now, it is important that we understand the word dozen does not mean 12. It is a grouping of 12. The reason why I say this is because if I say 3 dozen, does that mean 12? Is 7 dozen 12? 12 dozen 12? 9 dozen is 12? No. Dozen means groupings of 12. So if I say 3 dozen, I have 3 groupings of 12. 8 dozen? Well, 8 groupings of 12. Now this seems obvious, but when we start talking about the mole, people start freaking out. So when they say 4 mole, people think, oh, mole, 6.02 10 to the power 23. No. 4 mole means 4 groupings of 6.02 10 to the power 23. Just as 3 dozen is 3 groupings of 12, so 3 times 12 is 36, 4 mole is 4 groupings of 6.02 times 10 to the power 23, which is 2.40 times 10 to the power 24. So throughout this lesson, I will be making comparisons between the mole and the dozen, because they both serve the same purpose, grouping big numbers to make them more manageable. So if you have a pretty good understanding of the word dozen, you also have a very good understanding of the word mole. The only real difference between the two is that one is a nice pretty number and the other one's an ugly number. That's it, so don't freak out. Now, people don't normally think there's an equation for the word dozen, but there is. I mean, if I have 36 eggs, how many dozen do I have? Well, 36 eggs divided into groupings of 12 gives me 3 dozen. Well, it's the same with the mole, but instead of a nice pretty number 12, you get this ugly number over here, Avogadro's number. So if I have 3.60 times 10 to the power 24 sodium atoms, well, divided by Avogadro's number, gives me 5.98 mole of Na atoms. Now, there are several things to keep in mind. Thing number 1, mole, M-O-L, is the short form for mole, M-O-L-E. I know, saves you so much more time. Secondly, some students go, ooh, 5.98 decimals, that's weird. No, it's not weird. You can have decimals for dozens as well. I can have 2.5 dozen, or 3 3/4 of a dozen, etc., etc. It's just that we rarely use decimal numbers with dozens, but you're going to be using decimal numbers quite a bit with the mole. Now, the other thing I want to keep in mind is that the word dozen doesn't have to be related to food. I mean, usually we talk about it in terms of a dozen donuts or a dozen eggs, but it doesn't have to be food-based. It can be a number of whatever you want. Dozens of tires, dozens of boxes, dozens of monkeys, whatever. Well, similarly, the mole doesn't have to be just for chemistry. You could ask for a mole of Timbits. But just so you know, it would take billions of years for us to create this many Timbits. And so because Avogadro's number is so big, it's really only useful for dealing with atoms because there's so many of them. Now the last thing to keep in mind, whatever you're counting, that's what you're grouping. So if you have number of monkeys, then you're talking about dozens of monkeys. If you're talking about eggs, then it's dozens of eggs. Well, it's the same thing down here. If you're counting sodium atoms, then you're dealing with moles of sodium atoms. You can't be counting waters and say mole of oxygen. That would be like counting cars and then saying dozens of tires. Yes, the tires are part of the car, but you're counting cars, not tires. So the oxygen is part of the water, but we're counting water, not oxygen. But if I wanted to convert from cars to tires, I would have to set up a ratio. The same goes for water and oxygen. Got to set up a ratio. But we'll worry about this later in the lesson. So for now, just remember, whatever you're counting here is what you're counting here. Don't mix and match. Alright, now that we have the equation for the mole, let's see what we can do with this. The official equation is that the number of mole is equal to number of particles divided by Avogadro's number. Now down here I said number of whatever, but whatever is not really a very good technical term, what we're counting typically is going to be atoms, ions, or molecules. And the official term for those are particles. Secondly, Na, Avogadro's number, is just a short way of writing out 6.02 times 10 to the power 23. Alright, so let's try a sample question. If I have 4 mole, so where should I put this number? Should 4 mole go under mole, particles, or Na? Well, it's definitely not Na because Na is 6.02 10 to the power 23. Whoops, this one seems to be a mistake. That should be 10 to the power of 23, not 1023. I'll have to fix that later. But if you're ever confused about where these numbers should go, cover it up and just replace it with the word dozen. So if I have 4 dozen calcium atoms, how many atoms do I have? Well, in that case, I put the 4 dozen down here. But I'm not really working with dozens. I'm working with mole. So I have this variable now, 4 mole. I have this variable now, 6.02 10 to the power 23. Let's solve for this one. So rearranging the equation, I'm going to take Avogadro's number, multiply it out on this side. So now it's 4 times 6.02 10 to the power 23 is equal to the number of particles. And I get 2.41 times 10 to the power 24. Now don't forget, we're talking about 4 mole of calcium atoms. So it's calcium atoms on this side, then the particles we're looking at aren't ions, aren't molecules, they are atoms. So we have to say 2.41 10 to the power 24 atoms of calcium. Alright, so try these ones out. The answers are at the bottom. I'm going to move ahead. So, if I have 84 cars, how many dozen cars do I have? So how many groups of 12 do I have? Plugging this information into the equation over here, 84 cars divided by 12 equals 7 dozen cars. So remember, if we're counting cars on this side, we're counting cars on this side. So over here, if I have 4.214 times 10 to the power 23 atoms of calcium, how many mole of calcium atoms do I have? Or rather, how many groups of 6.02 times 10 to the power 23 do I have? So I'm going to take this number and place it under particles, because that's what I'm counting, atoms of calcium, divided by 6.02 10 to the power 23, and that gives me 0.7 mole of calcium atoms. Now, another thing I forgot to mention is that sometimes these calculations give students a little difficulty because their calculators are stupid. Now, there's nothing wrong with having a stupid calculator, but you have to understand that the calculator is dumb. It will only do what you tell it to do. It doesn't know what you want, it only knows what you told it to do. And so it's very easy for the calculator to misinterpret what you asked. Case in point, some students may type this into their calculator, 4.214 times 10 to the power 23, divided by 6.02 times 10 to the power 23, and they might get this number, 7 times 10 to the power 45. But the answer is supposed to be 0.7. The problem with typing this out in the calculator is that when you punch in 4 decimal 214 times 10 exponent button 23 divided by 6.02 times 10 exponent button 23, the calculator might interpret this as this instead. 4.214 times 10 to the power of times 10 to the power of 23. But if you push the divided by button now, the calculator is stupid. It doesn't know what you want. It will think the division sign is still within the exponent portion over here. So when you continue typing in 6.02 10 to the power 23, you end up with an exponent to another exponent, resulting in a super duper high number. So to avoid this situation, put brackets around each number, and now the calculator knows, oh, this is one number and this is a separate number instead of one giant long string. Now the calculator won't misinterpret what you wanted. Alright, so just watch out for these problems when you're dealing with scientific notation, and you will be dealing with scientific notation quite a bit in this course. Alright, try these questions out. Answers are at the bottom. Let's move ahead. Ratios. We use ratios when we're trying to convert one thing into another. So for instance, if you have 84 cars, I would put this 84 down here because that's what I'm counting. Well, 84 cars divided by 12 equals 7 dozen. But is this 7 dozen cars or is it 7 dozen tires? Well, because I start off with cars, this one must be cars. But the question doesn't ask for how many dozens of cars I have, it's asking for how many dozens of tires do I have. So I need to set up a ratio of cars to tires in order to convert this dozen of cars into dozen of tires. Now I'm going to cross this out for a second and put in 7 dozen cars under the cars column. Now I know the ratio of cars to tires is usually 1 to 4, so one car should have 4 tires. I'm going to ignore the spare tire. But let's just stick with 1 car's 4 tires. So there's 4 times as many tires as there are cars, so I have to multiply by 4. So if 1 car has 4 times as many tires, 7 dozen cars should have 4 times as many as well. 4 times 7 gives me 28 dozen tires. So I was able to take information about one thing, cars, and then convert it into information about something else, tires, using ratios. Now this is just one way of doing things. I can get the same answer, 28 dozen tires, by going around the other way, placing the 84 cars into the ratio first. Again, I know there are 4 times as many tires as cars, so it's a 1:4 ratio. So if I have 84 cars, well, 4 times as many tires. 4 times 84, 336. I can then take this 336, divide it by 12, and I end up with 28 dozen. But again, this time, because I started off with tires, I end up with tires. Same answer. So it doesn't matter if you plug it into the ratios first and then solve, or plug it into the equation first, then do the ratio afterwards, you get the same answer. Just make sure that if you're counting tires, your dozens are dealing with tires. You can't just turn tires into cars or cars into tires, not without doing your ratio. Now, if you understood how to do this using dozens, cars, and tires, you should also be able to understand how to do this with molecules, atoms, and Avogadro's number. Oh man, I messed that one up again. So this one should also be 10 to the power 23, not 1023. Where am I getting these errors from? Anyway, it's the exact same thing as this. So what we're going to do now is I'm going to have you plug it into the ratio first, and then once you've got your number, punch it out into the equation and solve. So if I have 2.709 times 10 to the power 24 molecules of H2SO4, how many mole of oxygen atoms do I have? So you'll notice they give you information about one thing, molecules of H2SO4, but then they ask you for information of something else, atoms of oxygen. It's just like giving you information about cars and asking for tires. So let's plug it into the ratio first. I know that for every 1 H2SO4 molecule, there are 4 oxygen atoms. So it's a 1:4 ratio, just as every 1 car has 4 tires on it. So going from here to here is 4 times as much, while going from here to here is 4 times as much as well, 1.08 times 10 to the power 25. Now that I've converted it into oxygen atoms, I can plug into the equation. 1.08 times 10 to the power 25 oxygen atoms divided by Avogadro's number, 6.02 10 to the power 23, gives me 18 mole of oxygen atoms. So remember, it started off with oxygen atoms, it must end off with oxygen atoms. The only way to convert between the two, ratios. Alright, try these questions on your own, answers are at the bottom. Okay, now our next topic is that of molar mass. So far all we've done is turn big giant ugly numbers into much smaller, more manageable numbers. But the problem is these numbers still aren't meaningful. Like 18 mole of oxygen atoms, what does that look like? What does that look like? Is that about the amount of oxygen atoms you would find in a test tube? Or in a big balloon? Or in a shipping container? How much is 18 moles of oxygen atoms? What does it look like? So this number, although smaller or more manageable than this guy, is still meaningless to me. To give it meaning, we need a conversion factor. So let's say I'm going to watch a movie in Sweden for some odd reason. And when I get to the box office, they tell me that one ticket is about 24 kronas. Is that a good deal? Is 24 kronas worth the price of admission? I don't know, because I'm not familiar with the krona. I need to compare it to something a little more familiar to me, like the Canadian dollar. In this case, 24 krona is about 350 Canadian. So is this a good deal? Absolutely. Well, that's what the molar mass is. It's a conversion factor that allows us to convert from moles into grams. Grams I understand. Grams I can measure out and see with my own eyes. Moles, on the other hand, I can't. Now, the molar mass can be found on the periodic table for any element. Essentially, the atomic mass is the molar mass. Instead of using the atomic mass unit, we can now say grams per mole. Meaning, if I had 1 mole of oxygen atoms in my hand, so that's 6.02 times 10 to the power 23 atoms of oxygen sitting in my hand, they would weigh 16 grams. And vice versa. If I had 14.01 grams of nitrogen atoms sitting in my hand, I would have 6.02 times 10 to the power 23 atoms of nitrogen sitting in my hand, or 1 mole of nitrogen sitting in my hand. So the molar mass is a conversion factor, allowing us to convert from the unrelatable world of atoms with their big giant numbers and moles all into something that we can understand, we can recognize. Grams, mass. So if I had 3 mole of helium sitting in my hand, how many grams would that be? Well, if each mole weighs 4 grams and I have 3 moles worth, 3 times 4 equals to 12 grams of helium. And that's where we get this equation. The units for molar mass is measured in grams per mole, and grams is the unit for mass. I can then rearrange this equation into this. Now we have 2 equations for calculating the number of moles. Mole is equal to mass divided by the molar mass, and mole is equal to the number of particles divided by Avogadro's number. That is how important the mole is to us as chemists. Guaranteed in this course, if you have no clue what to do, convert to moles. That's usually the first step in a problem. 90% of the time, the first step is convert to moles. Even if you have no clue what you're doing, and even if that's not the first step, convert to moles and I will give you part marks for that. The only time I won't is if I give you moles and you give me moles back. That doesn't really help you in that case. But seriously, even if you have no clue what to do, the first step is usually convert to moles. So far you've got 2 equations that can do that, but by the end of the course you'll have about 4 or 5 different ways to convert to moles. Alright, so let's get back into it. So the molar mass can be found from the periodic table. The molar mass of iron is 55.85. So 55.85 grams per mole. Now if I look at chlorine, because chlorine is diatomic, I have to multiply its molar mass by 2. So 35.45 times 2 is 70.90 grams per mole. Now the same thing applies for big giant compounds and molecules. Just add up the molar masses of their individual atoms. Magnesium is 24.31, but because there's 3 of them, multiply it by 3. Phosphorus is 30.97, but because there's 2 of them, multiply it by 2. Oxygen is a 16, multiplied by the 8 of them. Add them all up, and you get a molar mass of 262.87 grams per mole. Meaning, if I had 6.02 times 10 to the power 23 compounds of magnesium phosphate sitting in my hand, or 1 mole of magnesium phosphate sitting in my hand, it would have a mass of 262.87 grams. Alright, let's take a look at the next question. If I have 2.02 grams of hydrogen atoms, how many mole of hydrogen atoms do I have? So let's work backwards. I want to calculate the mole of hydrogen, but we have 2 equations to calculate moles. Mole is equal to number of particles divided by Avogadro's, and mole is equal to mass divided by molar mass. Which one should I use? Well, you'll always have Avogadro's number because you're going to memorize it, 6.02 times 10 to the power 23. And you can always access the molar mass because you have the periodic table. So when I look at the periodic table, hydrogen has a molar mass of 1.01. So in both cases, I'm missing the top, except over here the question says 2.02 grams. Now, should 2.02 grams go into particles or under mass? Obviously mass, because grams is a measurement, a unit of mass. So punch that in, and you get 2 moles of hydrogen atoms. You'll notice that the grams unit gets cancelled out, leaving you with the mole. So keeping the units is an excellent way to double check your work to make sure that your equation makes sense. Alright, so try these questions yourself. I believe the answer is all the way at the back of the page over here, so double check to make sure you're on the right track. And let's move on to the last question over here. Now this question requires you to use both equations. Take a look at this. I have 7.5 grams of iron, so I'm going to write that in. And it's asking me for how many atoms of iron. And that would go under number of particles. So they're giving me information to use one equation, but asking me to solve for a second equation. And we can do this because the number of moles acts as a middleman. Once I solve for the number of mole here, I can take this number, plug it in here, and then solve for the number of particles. Now the molar mass of iron I can find from the periodic table, 55.85. Dividing these 2 numbers, and I get 0.1343 moles of iron. Now be careful, don't start rounding your numbers during the calculation, only round your final answer, alright? If you start rounding too early, your errors will magnify up the chain. So I recommend keeping about 3 or 4 sig figs, I like 4 usually, and then only rounding my final answer when I get to the end. In this case, the final answer will only have 2 sig figs. Alright, so now that I have the mole of Fe, I can plug it into this equation. And since I know that Avogadro's number is 6.02 times 10 to the power 23, I can now solve for the number of particles. 0.1343 moles of Fe multiplied by 6.02 10 to the power 23 gives me 8.1 times 10 to the power 22 atoms of iron. Alright, and that is our introduction to the mole. Make sure you double check your answers. If you want even more practice, I recommend this worksheet over here. Answers again are on the back, so please make sure you double check your work. There's no point, again, doing everything only to find out you're all wrong at the very end. Now, the great thing about this particular worksheet is that it's freaking confusing, but that is by design. They have purposely made it wordy and confusing so you can practice your reading skills. Like, for instance, how many molecules are in a mole of molecules? Whew, that's mind-warping. In any case, my recommendation, like I said, if the word mole confuses you, cover up the word mole, replace it with the word dozen, and you'll feel a lot better reading it now. How many molecules are in a dozen of molecules? Then once you understand what you want to do, replace the number 12 in your calculation with the number 6.02 10 to the power 23. Alright, so give these a try. If you have any questions, come see me.